Hi everybody, this is Dr. Nigro with the Chem Calculations screencast. This screencast is going to look at buffers, what buffers are, their capacity, and then how to determine the pH of a buffer system. All right, so let's start with the definition. A buffer is a solution that resists changes in pH when an acid or base is added. All right, so if you have a solution and you add some acid and the pH stays relatively stable, or you have a solution, you add some base and the pH stays relatively stable, then you have to have a buffer. It is buffering that addition. All right, these solutions always contain a combination of a weak acid base conjugate pair. All right, so you could use acetate and acetic acid. You could use nitrite and nitrous acid. You could use any acid or base combo that does not appear on our strong acid or strong base list. Strong acids and strong bases do not buffer, they just react. All right, so there's no buffering there. You can't have both the acid and the conjugate base present, or both the base and the conjugate acid present, because they will not undergo equilibrium between the two. All right, so we need to be aware that we need that weak acid conjugase pair. All right, and these can be formed by dissolving salts in solution. All right, what do I mean by that? Well, let's say I have a source for acetic acid, but I need that conjugate base. Maybe I go into my stockroom and I get some sodium acetate. So when I dissolve the sodium acetate, that produces acetate ions for me, which is my conjugate base. So then that plus the acetic acid would give me a buffer. All right. And as I said, you cannot include conjugates of anything strong. All right, now let's talk about a couple definitions that go along with this. Let's talk about the first one is buffer capacity. Oops. All right, so buffer capacity is a measure of how much acid or base the buffer can absorb without changing pH. All right, generally speaking, the higher the concentration of the components, the greater the capacity. All right, and that makes sense. If you make a buffer and it's 1 molar in its components, that's going to have way more ions present to interact with acids and bases than if you make one that's 0.1 molar. All right, so the higher the molarity of the solution, of your buffer solution, the higher the capacity is going to be. All right, when choosing what conjugate pair to use, all right, keep in mind that your buffer is most effective when the desired pH of the system equals the pKa of that acid. All right, so choose components with that pH value in mind. All right, if you need a buffering system to hold the pH value around 7, all right, which is what we need in our bodies, all right, then we're going to choose a buffering system that has a pKa value of around 7, all right? That's going to be the most stable for us. All right, now, how do we calculate the pH of a buffer system? All right, because we've got acid and base present, so it can be a little tricky. Well, lucky for us, we have a formula. It's called the Henderson-Hasselbalch Equation. I actually love this equation. Well, to be honest, I love everything about acids and bases. They're very interesting and so important in your body. All right, but for this one, the pH is equal to the pKa of the acid plus the log of the ratio of the concentration of the base, divided by the concentration of the acid. All right, so if you look at this formula, when the concentration of the base equals the concentration of the acid, all right, then the pH of our buffer equals the pKa. That's because the log of 1 is 0, so pKa plus 0 is pKa. All right, you can also see, all right, that as this ratio goes up and down, that's either going to add to the pH or take away from the pH. So you can use the formula to make some predictions about that as well. All right, generally speaking, all right, if the concentration of the base is greater than concentration of the acid, then the pH should be greater than the pKa. And that kind of makes sense. We have more base present than we have acid. All right, and then vice versa. If the concentration of the base is less than the concentration of the acid, then the pH should be less than the pKa, which makes sense. Well, we got more acid than base, so we should see a drop in the pH. Okay, so let's try a couple problems. All right, first we're going to calculate the pH of a solution that's 0.5 molar acetic acid and 0.5 molar sodium acetate, and we've got a Ka value of 1.8 times 10 to the negative fifth. All right, so I know it's a buffer because I've got acetic acid and acetate, and that is a conjugate pair. All right, so I'm going to need to use the Henderson-Hasselbalch equation to make this pH calculation. So pH is going to be equal to the pKa plus the log of the concentration of base divided by the concentration of acid. All right, so first I need pKa. Well, I know Ka, and I know that pKa is the negative log of the Ka. All right, so the negative log of 1.8 times 10 to the negative fifth is going to give me a pKa value of 4.74. So there's my pKa. All right, for my concentrations, my concentration of acetic acid is given. All right, sodium acetate has a formula of NaC2H3O2. So you can see from the formula, there's one ion of acetate per molecule of sodium acetate. So if I have a 0.5 molar sodium acetate, then I have 0.5 molar acetate. All right, so pH is equal to 4.74 for my pKa, log of 0.5 molar for that acetate, 0.5 molar for my acid, so I'm going to get a 1, and the log of 1 is going to be 0, so this is a case where the pH equals the pKa. Okay? All right, let's look at this next one. What is the new pH after 0.02 moles of solid sodium hydroxide is dissolved in 1 liter of the buffer solution? All right, so this is talking about this buffer solution. Oops. All right, so that's good to know. Now, we have a reaction this time. All right, so we have a base that's being added, so we'll put the acid, oops, I forgot, there we go, H3O2, aqueous plus NaOH, aqueous, all right, in equilibrium with NaC2H3O2, aqueous plus H2O liquid. All right, so this is what we've got. All right, let's start our ice chart with what we have initially. All right, so I have 0.50 molar. All right, now I need to figure out what the molarity of this NaOH is. Oh, well, it's in 1 liter. All right, so 0.02 divided by 1, so 0.02 molar of that sodium hydroxide. The water will be in excess. All right, and I have 0.5 molar of that acetate. All right, so I'm going to use all of that added base. So 0.02 molar minus 0.02 molar plus 0.02 molar. All right, so this becomes 0.48 molar for the acid, 0 for that strong base, and then 0.52 molar for the conjugate. All right, so by adding base in, we've used up a little bit of the acid from our buffer and formed a little bit more of our conjugate base. All right, so again, a buffer is still present because I have amounts of an acid and its conjugate base, and they're weak. So I need that Henderson-Hasselbalch equation again. All right, so pH equals pKa plus the log of the concentration of base divided by the concentration of acid. All right, same pK as before, 4.74 plus the log. Now this is going to look a little different. It's not 1 anymore. So it's 0.52 molar for the base, 0.48 molar for the acid. All right, when I plug that in, I find that the pH is now 4.77. All right, so it's gone up a little bit, not a lot, not a lot. I mean, we added some strong base, so if we added that to water, that pH would have jumped straight up to 12. All right, but here it only went up by 0.03 pH values. All right, now I'm not surprised it went up because we did use up some of the acid in our base and form a little bit more of our conjugate base. All right, so it going up was okay. All right, but it not shooting up is what tells us it's a buffer. All right, let's look at this next one. A buffer is prepared from 60 milliliters of a 0.1 molar NH3 solution and 40 milliliters of a 0.1 molar NH4Cl solution. What is the pH of the buffer solution? The Kb for ammonia is 1.8 times 10 to the 5th. All right, so let's start with concentrations. All right, so we're going to have 2 solutions being added together. So we're going to have some dilution going on here. The total volume at the end is going to be 100 milliliters. So we're going to need to account for that dilution. So let's start with NH3. All right, so we're going to have 60 milliliters times 0.1 molar equal to 100 milliliters times the diluted volume. All right, so concentration. The diluted concentration is 0.06 molar. All right, so that's the concentration of NH3. All right, now let's look at the concentration of its conjugate acid, which is ammonium. All right, so we have 40 milliliters of that solution. Now it's 0.1 molar for the salt, but it's a 1-to-1 ratio between that ion and that salt. So we can say we have 0.10 molar of that ammonium. That's going to be equal to 100 milliliters and a diluted molarity. All right, so the molarity of the ammonium in my new solution is going to be 0.04 molar. So there are my 2 concentrations. All right, now why did I do all that? Because I got a buffer. I'm going to use the Henderson-Hasselbalch equation, and I'm going to need those values. All right, so as a matter of fact, let's write that formula to remind ourselves. So pH equals pKa plus the log of the concentration of the base divided by the concentration of the acid. All right, now the next part is the pKa. All right, I have Kb, but I don't have Ka. All right, so I'm going to need to convert Kb to Ka. All right, so remember, Ka and Kb are related through Kw. So Ka equals Kw divided by Kb. Kw is 1 times 10 to the negative 14th. We'll divide that by 1.8 times 10 to the negative 5th. And we have a Ka value here of 5.6 times 10 to the negative 10th. All right, now that's not quite what I need. I need pKa. All right, so I'm going to take that and calculate pKa, the negative log of my Ka value. All right, so we get the negative log of 5.56 times 10 to the negative 10. Oh, I should use, for digits purposes, I should be using 5.6 here. Let's fix that just so we don't carry too many. 5.6. All right, so the negative log of 5.6 is something. I did my calculation earlier and used 5.56, but let's be accurate where we can. So 5.6 to the negative 10th. 9.25. So 9.25. So that is our pKa. All right, so we go back up. Oops. 9.25 plus the log of the concentration of the base, which is NH3, so 0.06 molar, divided by the acid, 0.04 molar. All right, we plug everything in, right, and we find that the pH here is 9.44. All right, so we asked ourselves, is that reasonable? It's a little bit higher than the pKa. All right, and I think that's reasonable because we have more base present in this buffer solution than we do acid. So I'd expect it to be a little bit above the pKa value. All right, number 4. If 50 mils of a 0.1 molar HCl solution is added to 100 milliliters of a 0.05 molar phosphate buffer at pH 7.2, what is the resultant pH? And what are the concentrations of our two buffer components in this final solution? And there's our Ka. Okay, so we again have a dilution issue, which I'm going to start with. Whoops. All right, so we're going to have a V total once these two solutions are added of 150 milliliters. All right, so that means the concentration of HCl is going to be 50 milliliters times 0.01 molar equal to 150 milliliters times that dilute molarity. All right, so the dilute molarity for HCl is going to be 0.0033 molar. All right, so that's my HCl, which means that's my H plus. All right, now, all I know is I have a buffer. I don't know much about the amounts within that buffer, but I can determine the concentration after dilution. All right, so I have 100 milliliters times 0.05 molar, and that's going to be equal to 150 milliliters times my unknown molarity. All right, so the molarity of the buffer after dilution is going to be equal to 0.0033 molar. All right, so these are our two concentrations. All right, now, what are we looking for? What is our unknown? All right, well, really what I'm trying to figure out is what is the ratio of my two components? What is that concentration of base versus acid? Because if I can figure that out, then I will know what the amounts of each of these two things are within this 0.033 molar buffer solution. All right, so I'm going to use the Henderson-Hasselbalch equation to find that. So the pH is equal to the pKa plus the log of the concentration of base over acid. All right, and this is going to be my unknown. All right, which means I need the pKa. I have the Ka, so the pKa is the negative log of that value. So we plug that in and we get a pKa of 7.20. All right, now this solution initially had a pH of 7.2, right? The pKa is also 7.2. Oh, that should tell me something about that ratio, right? If the pH equals the pKa, all right, then I know that the concentration of the acid versus the concentration of the base must be equal, all right? All right, so if I subtract that 7.2 over, I'm going to get a 0 here, and I'll have the log of the base over the acid. And if I take the inverse log of both sides, I find that the ratio of acid to base is equal to 1. All right, so that means that each must have been 0.05 molar initially. And this is before dilution, which means that now each of them must be 0.033 molar. All right, so that is going to be my initial values that I'm going to be using. All right, so let's start by writing out a reaction. So if I look, I am reacting with an acid. This is an acid, so I need the base to react with it. No, I just did that backwards. No, that's right. All right, so HPO4 minus plus HCl is going to yield H2PO4 minus 2 minus plus Cl minus. All right, so that's going to be the reaction. The hydrogen ion from the acid is going to interact with the conjugate base of my buffer, reforming that conjugate acid. All right, so we set up our ice chart again. All right, so after dilution is taken into consideration, I have 0.033 mole. No, I'm missing a 0. 0.033 molar. Wait, what? Oh, no. All right. Sorry. The numbers are very similar. I just realized I made a mistake. All right. Up here, right, I did this wrong. This is off by a factor of 10. That's why I made a mistake. All right. And then for my HCl, 0.0033 molar. Then I'll have, oh, nope, I do have some of that present. 0.033 molar, and then none of my chloride ion yet. All right, we look at the two reactants. We lose all of the acid, 0.0033 molar. So subtract that out, and then I'm going to gain that on the product side. All right, so I subtract that out. I have 0.03 molar left of my HPO4 minus 2, none of that strong acid, and then I have 0.036 molar of my H2PO4, and then 0.0033 of that chloride ion. All right, but the chloride ion is irrelevant because that's the conjugate base of a very strong acid. All right, so what I've got in solution is some HPO4 minus 2 and some H2PO4 minus. That's a buffer system. All right, so again, I'm going to use the Henderson-Hasselbalch equation, where I have the pKa plus the log of the concentration of base over acid. All right, pKa is still the same at 7.20. The ratio is different this time, though. All right, so our base is 0.3 molar, and our acid is 0.36 molar. All right, so we do that division, take the log of that value, and then add that to our pKa, and we have a new pH value of 7.12. All right, that is lower than what it was for our pure buffer, right? Our pure buffer had a pH of 7.2. This is reasonable, right? I added in some acid. I used up a little bit of the base component of my buffer. So I have a decrease in my pH value because of that increase in conjugate acid concentration. All right. So that's a tricky one. I like it. It's a good problem. All right. But it does require you to really think about what's going on. What is the unknown that you have to find first? And then how can you use that to find what the question is asking for? Okay. All right. So again, buffers, just a special type of solution that contains a weak acid-base conjugate pair that when other acids or bases are added to it, they're able to absorb those acids and bases without having a very large change in their pH value. All right. The capacity depends on the molarity. The more molar or the more concentrated your buffer, the higher its ability to resist that pH change. All right. And then don't forget that Henderson-Hasselbalch equation, that pH equals pKa plus the log of the concentration of base over acid. You have to use that whenever you're determining the pH of a buffer system.